In this demonstration, we'll be using an IVI COM driver from Microsoft Visual C# language. To do this, we'll just create a generic project using all of the default settings. And since we need to call the external assembly, which is the IVI COM driver, we will go into the Solution Explorer and add a reference to that driver. Notice here that the IVI drivers, per the IVI standard, are all installed beginning with the term IVI, so you can see all the drivers here in a row. We have the Agilent 34410 we'll be using, and you can also see down here there's a IVI DMM type library installed as a part of the IVI Consortium deliverables, which we'll also use when we get to the class compliant interface. So having added the reference to that assembly, we need to specify the namespace. Notice that the namespace includes interop. That's because this is an IVI COM driver, and the COM interface requires an interop assembly to call it. Turns out the interop assembly and the way that's created is also specified by the IVI Foundation, so your COM drivers will include that, and they'll all basically work the same way because the primary options associated with creating that interop assembly are all specified. So, having done this, the next step is to get ourselves a reference to the object. So we'll just call it DMM, since we'll be conversing with a DMM. And that's a new Agilent 34410. So, to use that driver now, the first thing we need to do is initialize it, which is the point at which we specify the address of the instrument we'll be controlling, as well as some setup parameters. So that's done with an initialize call. Every IVI driver has an initialize call with the same signature. First parameter is the resource name, which is typically a Visa resource string. For GPIB instruments, it is always a resource string. So we'll just say GPIB 027 to put in a conventional address. This example will actually use the instrument in simulation mode, so it doesn't matter what we use for an address. The next parameter here is a Boolean for ID query. That specifies whether the driver should start out by querying the instrument to verify that the instrument it's connected to is one that it supports. Doesn't really make any difference for our application since we'll be in simulation mode. There's nothing out there to query. Next parameter is a reset. This allows us to reset the instrument as a first step, which is generally a useful thing to do, but if you've got an application that needs to pick up the instrument from a state that another portion of your program has left it in, or perhaps from a setup that was provided on the front panel, this would allow you to retain it. But by setting this to true, we would be resetting it. The final parameter here is a string, optional string, that allows us to specify some options. I'm recording. The final parameter is an option string. As a matter of fact, it's an optional string, as you can see here. And this string allows us to specify various options for the driver. In our example here, we'll just use it to turn on simulation by saying simulate equals true. Okay, the driver is now initialized and ready to go. So we'll configure the instrument to make a simple DC volts measurement, get that back and check it. So to do that, DMM, you notice here that voltage is an interface, has all of the setups for voltage. Similarly, this instrument has status and resistance and other various things that may be useful, but we'll just go in and make a DC voltage measurement. Notice that DC voltage and AC voltage are in separate interfaces because they are both configured a little bit differently. And you can see here various settings associated with DC voltage which this instrument provides. we'll just use the standard configure operation, which provides us with access to the basic settings that we'll generally need, and that's just range and resolution. So we'll put in a 2-volt range, and notice here that the resolution is an enumeration, so we'll take that enumeration and choose just the default resolution. Next, to trigger and get a reading back from the instrument, we'll go to the measurement interface, which is a standard interface specified by IVI, and we'll use the read method. The read method is conventionally something which provides both the trigger and extracts the result, as opposed to doing an explicit trigger and a fetch. And you see here from the signature prompt that the read method provides both a, well, that's off the screen. You can see that it returns a double array. That's because this instrument is capable of doing multiple measurements per trigger. In our case, we'll only be getting one result back because we haven't configured any of that. But if we go ahead and do the reading and declare object to contain that reading, and we'll declare readings since it's multiple values. Next, we can just print out that result that we've acquired. So we print that out with a conventional format, and notice that since readings is an array, we'll just print out the first member. And we've now got the result from the multimeter printed out. We're just about done with the program. We ought to do a console read line so it doesn't run off the end before we can see it. This appears to be a fairly complete program. We have one little problem still with it, and that is that we haven't closed the driver. If you fail to close the driver, various resources never get deallocated, which can cause problems later on in your program, especially if something later on in your program tries to access the same instrument and there's a connection open to it. That's fairly simply done just by calling close. Okay, that simple little program created our driver, initialized it, configured the DC voltage measurement, got a reading back, prints it out, and closes the driver. So let's take a look at it. We can see here that the reading return was 0, fairly uninteresting result. This is typical of what you will get back from an instrument in simulation mode because the instrument knows very little about the device under test and what might be a more realistic answer. So typically IVI drivers in simulation mode return 0 or a random number or something like that. This can still be very helpful in getting a program up and running because, as you can see, we were able to type in all the syntax that talked to the instrument and controlled it and run the program. The reading is meaningless, so if we wanted a more sophisticated simulation, we'd have to somehow pick up the control flow when we get the reading back and insert a more realistic simulated value. But even without doing that, the simulation capability is very useful. The next thing I want to take a little bit of a look at is the IVI compliant interface. So let's just leave that where it was, and I'm going to come in here before the close and look at creating a reference to an object that's now implements the IVI compliant interface. So our first step here is we'll specify the IVI DMM interop assembly. Notice that we didn't have to add another reference to the project because this assembly is also implemented by the 34410. But now, using that namespace, we will declare an IVI DMM, and we can basically just set that equal to the DMM and get a reference to that same DMM. But what we will do is we will specify here with a cast that it needs to go off to this DMM object and return the IIV DMM interface, so the first I representing an interface, and the IVI DMM, of course. So now we've got IVI DMM that is a reference to the IV standard DMM definition, which isn't quite as rich as the instrument-specific one, but is, of course, has the asset of being common. So now when we type in IVDMM, we see a slightly shorter, slightly different list of operations. And using the IVDMM, we've got to configure right at the root node. Recall with the DMM that we were found the configure function underneath voltage and DC voltage. So it was a very custom configure function. In this case, our configure function starts out by specifying what the measurement function is. So no longer are we getting it as a DC voltage.configure, but we're specifying generically that we're going to do DC voltage again, but as a part of this common signature. And of course we can specify a range and a resolution. Now our resolution is a voltage setting instead of just the default setting based on the instrument interface. So in this case the configure function is a little different, but we can accomplish very similar measurements. Using the IV standard one, you've basically written something that provides information that could be used by any DMM to configure. Obviously the 34410 has specified, well, this is my default resolution or my high resolution, so that's not portable to other instruments. By using the IV interface, things have to be specified in a way that may not be quite as convenient, but they are defined in a way that can be used with any instrument. Now, having configured that DMM, we'll find that the readings are very similar. So we'll say ivdmm.measurement.read. So very similar to what we had before, but now notice that our read this time has a timeout milliseconds parameter, so we'll say 1000 milliseconds. And the other thing to notice about the read in this case, let me bring up that IntelliSense again, is that it returns double instead of an array of doubles. So the IVDMM doesn't return an array the same that the 34410 did, so we'll just have to, when we get a reading back, it'll be a single value instead of an array. And of course the value that we get back from that, still coming from the same driver, still being in simulation mode, should be about the same thing. But we'll print that out also from the IVDMM interface. So now we have something very similar. 3 similar lines here corresponding to the lines that were up here. And we can run this and should get a similar result. We see we got the reading from the IVDMM interface was 0. So this is basically what we would get in a simple application that needed to use the common interface. Notice here that to use this, we still need to create the DMM using knowing the Agilent 34410, and we didn't initialize it again, but that would look the same. The key element here, though, between the difference between the two, is that we've specified here that common interface. So there are provisions in Ivy that will allow you to create the DMM from a system database without specifying the actual type of it, allowing your program to be completely independent of the instrument. We won't go into that mechanism in this example, but you can see here that the API is a little bit different. The one here is perhaps a little bit richer, but this specifies things in a way that can be used for any DMM. Thank you for your interest in this Ivy training video. There are several other videos available on the Ivy Foundation website, along with Getting Started guides and Getting Started videos. All are available at the URL here, http://www.ivyfoundation.org/resources. Thank you.